Okay, this is lecture 29. We just finished talking about the process process in lecture 28. And so this is just going to give some examples. And so these examples will be some that'll be similar to what you might see on assignments. And so to kind of give you an idea of how you look at the process, how you look at finding probabilities of something happening. If you're modeling with something with the process, how do you find the probability that something's going to happen? Or it also will look at like waiting times. So like, and those would follow an exponential distribution. So we'll be looking at waiting times like in a post office, or you know, if you go in someplace, you know, so different times where you talk about waiting times. Lots of times people will model those with exponential random variables. So these are examples of that as well. Okay, so just reminding you a process. So in the previous lecture we talked about the process. It has a Poisson distribution with parameter lambda t. So if you're looking at the probability that x of t for some time t is equal to some given value n, then you can find that by just looking at the Poisson distribution with this parameter lambda times t, and substituting in the n value that you're interested in, what the rate is that you assume, and the time that you're interested. So just some brief reminders about the Poisson process. So if you're looking at the expected value or the mean, then that's just going to be your lambda t. It's just your parameter. And again, the variance for the Poisson distribution, the expected value and the variance are the exact same thing. So they're both lambda t. So remember, our holding time followed an exponential distribution. So we'll also be looking at exponential distributions kind of throughout. So in lecture 27, we proved that for any continuous time Markov chain, the holding time, which we represented as Ti, was exponentially distributed with rate lambda I. So it has this distribution here, lambda I e to the minus lambda I t, t greater than or equal to 0. So here for the exponential distribution, it's different than for the so don't get confused, it's different for the Poisson distribution. So each distribution has its own way of calculating the mean and the variance. For the exponential distribution, the expected value is 1 over lambda I, so 1 over the rate. And your variance is just your expected value squared. Okay, so the CDF for the exponential distribution is given by this function f of t here. So we have, so for any so if you want to find the probability that your holding time or some time t is less than or equal to some given time. So if you want to find out, you know, how long it's going to take. So if you assume that your waiting time is going to be less than, let's say, 2 minutes, if you're on a phone call with somebody, for instance, then you can calculate the probability that your waiting time or your holding time is less than or equal to something by just looking at f, like CDF evaluated at t1. You can calculate the probability that it's in between two times by just looking at f of t1 minus f of t0. You can also calculate the probability that it's greater than some given value t0 as just 1 minus f of t0. So it's just e to the minus lambda t0. So these are all going to come into play when you're doing some of your homework problems. So we already have that. Okay, so additional properties of an exponential distribution. So remember, you have this memoryless property. So this is one of those where it doesn't matter what time you came from, the probability that, so it doesn't matter what s you were at before, or what your probability that you're given t is greater than some s, that you've gone a certain time, it's memoryless, and so it's just simply the probability that your time is greater than that little t, assuming like you're starting at 0. So only the time that is passed is necessary. Okay, so if you have two variables that are exponential, that follow an exponential distribution, and you're looking for the minimum of it, then the minimum also satisfies an exponential distribution, but the rate is different. So here, if you're looking at the minimum of two variables, is also an exponential distribution, but the rate is now you have to add the two rates together, the rate of each of them. So if you're looking for the minimum of several different random variables, then it's also an exponential distribution where the rate is the sum of the individual rates. And if you want to find out the probability that, let's say x is the minimum of xy, so you want to find out the probability that x is less than y, then in here, again, I'm assuming the probability of x is lambda here. So here I take my lambda, the probability of the one that I'm assuming is to be minimum, divided by the sum of the two probabilities. So I can extend this if I'm looking at like a bunch of them, then I can take the probability that xk is the minimum, so the rate of xk, so it's lambda k, all over the sum of all the rates. Okay, so an example of this. So you can probably read this for yourself, but we'll just kind of go through this. Okay, so assume Allison has a flashlight. It needs 2 batteries to be operational. She has an empty flashlight which she starts off with. She goes to the store, buys 12 functioning batteries, and we call them battery 1, battery 2, etc. So initially Allison puts batteries 1 and 2 into her flashlight to get working, and the batteries are assumed to fail one by one. Whenever the battery in the flashlight fails, the flashlight obviously stops working. She tests the 2 batteries, she takes out whichever one is bad, and she replaces the bad one with a good one. So she keeps the working battery in there, and then suppose that the batteries remain like new until they're installed, and the lifetime of the batteries in use in the flashlight are independent random variables which satisfy this exponential distribution, and in which they have a mean of 4 months. So we're going to let capital T be the time that the flashlight ceases to work. In other words, she's gone through all 12 batteries. And at that moment, one of the original 12 batteries will stop working. And then the last battery that's in there will be, we're going to call it battery N. We don't know what N is. N could be any of the first, second, third, fourth, etc. 12 batteries. So think about you're taking this flashlight, you're taking out one battery whenever it goes bad. I could have taken out battery 2, or I could have taken out battery 1 to begin with. Let's say I take out battery 2, so now I have batteries 1 and 3. Well, then the flashlight stops working again. Battery 3 could have gone bad. I take out battery 3, so now I have batteries 1 and 4. Now battery 1 could have gone bad, so I now have batteries 4 and 5, etc., etc. And so here we're saying we're letting N be the random variable that takes on the values 1 through 12. And it would be one of the remaining working batteries in the flashlight. Okay, so there's a couple different parts to this question. First is, what is the expected value of capital T? So whenever the flashlight is working, it has a remaining lifetime equal to the minimum of the lifetime of the 2 batteries in the flashlight. So because we're talking about exponential distribution, this lack of memory problem, then the minimum of 2 independent identically distributed exponential random variables, the minimum of that is also going to be exponentially distributed. And like we said before, so if you're looking at the minimum of 2 random variables that have an exponential distribution, it's also going to have an exponential distribution that has rate lambda 1 plus lambda 2. So in our case, we're going to assume that B1 has a rate of lambda 1, B2 has a rate of lambda 2. Then we can talk about the minimum of the 2 have a rate of lambda 1 plus lambda 2. Just what we did just a second ago. Okay, so in this case, if we're looking here, we were given this statement that says suppose the lifetime of the batteries are independent, each having a mean of 4 months. So we're given the mean. So let's think about what we know about the mean. So we need to find the rate. So we know that the mean is given by 1 over lambda I. We have a mean of 4, so we can find the rate lambda I. So here we have the expected value of our battery is 4, which means lambda I is 1/4. So now we assume all of them have the same. So to find the fact that when the flashlight stops working just one time, it's going to have a rate of 1/4 plus 1/4, or 1/2. So each time the exponential distribution for the life until the flashlight stops, each time you replace the battery, it's going to have a rate of 1/2. It's going to follow exponential distribution of rate of 1/2, which means it's going to have a mean of about 2 months. 1 over that 1/2 is 2 months. So if we have 12 batteries, there's 11 times that this flashlight will stop working because one of the batteries has stopped, one or the other of the batteries has stopped. So the expected value of our T is 11 times whatever that expected life is just for that of the battery. So we're going to have 11 times 2 months, which is going to give me 22 months. So we're assuming that we're going to go through all 12 of our batteries. We're going to have a non-working flashlight in 22 months on average. Okay, so what is the probability of the 12th battery, the one that remains working in the end? So what we're asking is the probability of the n equals 12. So here we have that the probability that x is the minimum is, remember this lambda over lambda plus mu. So what's the probability that we're going to have our 12th battery as our last one? So at the end, it doesn't matter whether or not 12 is paired with 1, 2, 3, 11. It doesn't matter what battery it's paired with. We're still going to have the same probability of 12 being the last one that remains. So the probability that n equals 12 is the probability that whatever other battery is in there is going to be the minimum between our 12th battery and whatever that battery is. So this is the battery that n is less than 12. We look at the two rates. The rate of n is 1/4. The rate of 12 and n is 1/4 plus 1/4. So we get probability that n is equal to 12 is just 1/2. And then we have what is the probability that the first battery will be the one that remains working. So we want to know the probability that capital N is equal to 1. So we want to know what the probability is that the last one is the one that survived. Well, if we think about it, what it has to do is the last one has to survive 11 times. So when we replace, when it stops working the first time, battery 2 had to have been the one that stopped working. Stops working the next time, battery 3 would have been the one that stops working. So it had to survive 11 times. And each time a new battery is put in there, it has a probability of 1/2 of surviving. Just what we did in the previous time. So it has the probability of 1/2 that it's going to survive whenever a new battery is put in. So it has to do this 11 times. So we're going to have 1/2 to the 11th, which is 1 over 2048. Okay, so example 2. Joe receives text messages starting at 10 a.m. at a rate of 10 texts per hour according to the Poisson process. You want to find the probability that he will receive exactly 18 texts by noon and 70 texts by 5 p.m. So this is exactly. Okay, so we want the probability that N2, so the text after 2 hours by noon, because we're starting at 10 o'clock, right? So this is our 0 time. So the text by noon is 18, and then the text by 5, which is 7 hours after our starting time, is 70. Okay, so let's think about this. If 18 of the texts arrive by noon, then we have 18 texts in the interval from 0 to 2. We want 70 total texts to arrive by 5 p.m. So that means that 70 texts are going to arrive in the interval from 0 to 7, because it takes 7 hours to get from 10 to 5. Or the other way we can think about this is there has to be 52 texts arrive after noon, so arrive between the interval 2 to 7. Because remember, we already had these 18 texts arrive by noon, so now we have 52 texts that needs to arrive in order to give us a total of exactly 70 texts by 5. So we want the probability that there are 18 texts in the interval 0 to 2 and 52 texts in 2 to 7. So in other words, the set N2 equals 18 and N7 equals 70 is the same as if we look at N2 is 18 and N7 minus N2. So how many we get for the whole 7 hours minus what we got in the first 2 hours is 52. Okay, so the intervals are disjoint, so we can multiply the probabilities together. So the probability of N2 equals 18, N7 minus N2 is equal to 52 is equal to the probability times the probability. Okay, so now here's a note. So N7 minus N2 is not the same as N5. Because how many texts we get in the interval 0 to 5 could be different than the number of texts we get in the interval 2 to 7. They still cover both 5-hour time periods, but they're not the exact same. What is the same, though, is the distribution. So same number of techs, or it's not the same arrivals, but the same possibilities, the same distribution are going to be the same. So because the distribution is going to be the same, then the probability that N7 minus N2 is 52, this is a 5-hour time period, is the same as this 5-hour time period. The probability is the same, not the actual interval. So putting together, we have the probability that we want to find is equal to this one. Remember, they behave like a Poisson process according to the Poisson distribution. It arrives at 10 techs per hour. So for N2 equals 18, we plug in 18 here. We have 2-hour time period. We have 10 techs per hour. Here we have our number of techs is 52. Again, 10 techs per hour. Here we're talking about 5 hours. So putting them together, we get our probability is 0.0045. So not really likely. Okay, and for the last example, starting at 6 a.m., customers arrive at Martha's Bakery according to a Poisson process at the rate of 30 customers per hour. We want to find the probability that 65 customers arrive between 9 and 11 a.m. Okay, so t equals 0 is our starting time. That's 6 a.m. And we want the desired property, so we want between 9 and 11 here. So we want between 9 and 11. 9 is 3 hours later, and 11 is 5 hours after we've opened. So we want N5 minus N3 to be bigger than 65, because we want more than 65 customers to arrive during this time interval. Okay, so using the same idea that the distribution is the same for equal length time intervals. It's not the same as we're going to get 0 to 2. It's the same as from 9 to 11. So 6 to 8 is not the same as 9 to 11. But the distribution is the same. So the probability that N5 minus N3 is greater than 65, we can say is the same as the probability of N2 being bigger than 65. So the probability that N2 is bigger than 65 is 1 minus the probability that it's less than or equal to that. So we know how to write less than or equal to. We can think of the probability of n being less than or equal to is the sum of all these probabilities that n is equal to 0, n is equal to 1, n is equal to 2, and adding up all these probabilities. So therefore what we get is the probability that we're looking for is 1 minus this probability that it's less, so we're going to sum up all the possible probabilities going from 0 to 65, assuming that what if we had, what's the probability of having no customers, what's the probability of having 1, probability of having 2, all the way up to 65. We sum all these up, and so here we're going the sum 0 to 65. This is our Poisson distribution, so the N2 equals K. We have 2 time hours. We had a rate of 30 customers per hour, and we have number K here, and so we sum all these up and we get 0.2355. Okay, so next time we'll talk about a few more examples.